maybe before getting into how the data might show this, because cosmic strings have never come up on the show in 200 episodes, maybe we should spend some time going into just what cosmic strings are.
All right. So if I would say to you cosmic string, and you would think, what the heck could that be? You'll probably have the right idea. So it means objects which are microphysically thin and astronomically long. So we are interested in loops of string that are maybe a few light years in length. There would be lots of them in our galaxy and intergalactic space everywhere. And the thickness of them is some tiny, tiny subatomic diameter, depending on the energy scale at which these cosmic strings exist. So what are they made of? Well, there are two possibilities. One is they are defects from phase transitions early in the universe. So they're kind of like defects in a crystal. So a crystal, the simplest situation is to have a very uniform lattice of atoms, but there can be a defect. There could be a line of atoms that are missing. So you have your crystal, and there's a million atoms across over here, a million, but now there's a million minus one. So how did you get from a million here to one fewer here? Well, someplace there's like a hole, places that things don't line up. And the crystal has some extra energy in that place where things don't fit. And it is very much the same idea that would be here, only it's not crystals. It's not discretely spaced things. It's some kind of field theory. There's some way that at an early time in the universe, there's a symmetry-breaking transition. The field goes from being uniform to being a little different in one place in the universe and another. And when the universe is cooled off, all the different ways in which it cooled off don't quite fit with each other, and so you end up with a narrow line going through space where things have not really cooled off and there's a high amount of energy there. So you could think of it as like a rubber band, something very thin, very springy. In fact, it's a sort of a relativistic rubber band. So when you pull on it, you put energy in, and that allows you to make more rubber, so to speak. So you can make it longer and longer as you go. So it doesn't have like a fixed length. You know, a rubber band, you say, well, this rubber band is 3 inches long or something, but a string could have any length. When it's in a loop, it's oscillating, it's moving at some decent fraction of the speed of light as it moves around in some complicated periodic path. So you could imagine your rubber band again. Take the rubber band, stretch it out in some complicated shape, toss it up in the air, and it's going to go like this. Not at the speed of light, though. Cosmic string is going to go like this at half the speed of light, maybe. So that's what it is. Very massive, very rapidly moving. These are the ingredients we need for gravitational waves. So that's how these cosmic string loops could contribute to the formation of a gravitational wave background that we might be able to see.
Okay, I've got a number of questions. So you said that they're microscopically thin, astronomically long. I mean, effectively one-dimensional is what it sounds like. And are these observable potentially with the naked eye, or what sorts of radiation might they emit?
Right. So in the simplest case, the string, it's very thin. It doesn't have much effect on anything. It has very, very high energy, but the very high energy is confined into this very narrow tube. So, if we had this string in between us somewhere, we wouldn't be able to see much. In fact, they produce gravitational lensing, So there is a very, very tiny bending of light. If the light goes on one side of the string versus the other side of the string, it might be bent by a very small angle that would be hard to observe. Strings which were very, very massive. So I should say the string has an energy scale. So it could come from physics at various different energies. And the energy tells you the tension of the string, which is the same thing. It tells you how much energy there is in a certain length of string. And since we don't know what process it is that might be creating these strings, we don't know what that energy scale should be. But it can be limited. The higher it is, the more gravitational waves there will be, and the more effects of all kinds. So at the beginning, for example, people looked at the cosmic microwave background. They looked for an effect called the Kaiser-Stebbins effect, in which the temperature of the cosmic microwave background that we observe with satellites like Planck would be different on one side of the string and the other. So that would be a line. So you could imagine those cosmic microwave background pictures that we've all seen. And on the picture, there would be some kind of a line, maybe a wiggly line, with things a little bit hotter on one side and colder on the other side. So that would be a very clear effect. That requires a pretty high energy scale. And that was never seen. Strings of that scale would produce a huge background of gravitational waves, which we would also have seen. So nanograv is now the limiting observation. It sets the tightest upper limit on what the energy scale of cosmic strings could be. And so we know because of that, until you get into some even more exotic kind of strings, but the simplest kind of strings, which don't have ends, which come in loops or infinite strings, these strings would be seen in nanograv before you would see them in the microwave background. Or before you could see, for example, lensed galaxies. So there was a kind of a fuss a while back with the idea that there were two galaxies that looked very, very similar right next to each other. And maybe they were really one galaxy, and what we were seeing was two images of the same galaxy due to the lensing of a cosmic string. Well, eventually, they took a closer look at it with the Hubble Space Telescope, and it turned out just to be two galaxies that looked kind of the same. So that's another thing you could see, but we kind of knew that that was wrong at the time. I mean, it was very exciting, but we kind of also knew it was not likely to be really cosmic strings. And the reason is that the energy scale that would be required to have produced that gravitational lens was too high compared to other experiments, and it really was already ruled out. So that's the kind of things that we expect to look for. Now, cosmic strings may have cusps. The cusp is a place where the string forms itself up into something looking like this, moving very, very fast, nearly the speed of light in this direction. And it's possible that could send out a beam of radiation here, making some sort of a flash. Again, we don't expect that because the dominating effect is different. And so the limits that are given by nanograv make that very unlikely, unless you go into more complicated models. There are lots of more complicated ideas, superconducting cosmic strings that could get electrical currents on them and then produce electromagnetic radiation from these cusps. They're kind of a wide range of possibilities.
Well, again, there are many things that I'd like to ask, but I think that the next thing that I should ask is what symmetry breaking transitions are, just because having a sense of why there might be cosmic strings in the first place might ground those further questions better.
All right, difficult to do with no visual aids here. So let me give a sort of an example. Suppose you have a bunch of little needles or something, and they're all stuck in a lattice on a board. Okay, so here's this flat thing. You got these things that are all sticking up, okay? And they're all connected with little springs or rubber bands or something at the top. Under the force of gravity, they kind of all like to fall down. So they can all fall down the same way. Okay, Everything is just fell to the left. They can fall to the right, towards you, towards me, whatever. But now suppose that all these things happened to fall down not in a uniform way. So these ones fell down like this, these ones fell down like that. So just look over here at the ones that fell down in this direction. Looks great. They're all falling down. They all fell down the same way. All the little springs that hold the tips together are fine. They're all happy. Look at the ones that fell the other way over here. They're happy too. But there's a problem. Because somewhere between the ones that fell this way and the ones that fell that way, there's some place in the middle. And these guys have a problem. Which way are they going to go? Well, they'd like to go this way to match those so that their springs would be happy. They'd like to go this way to match those. And you could say, well, okay, what if I make it into a curve? These are all falling down. These are falling down. These are falling down. Fine. But somewhere in the middle, one of these needles is standing up because it doesn't know which way to go. That's the symmetry break. At a symmetrical state, everything is up, same everywhere. We broke the symmetry by having them fall down. We broke it in different ways in different parts of the universe. Some fell one way, some fell the other way, and the result is a defect. There's a place where the thing didn't fall down. It's standing up, and now this one's standing up, and this one more and more and more are falling down, and these springs are all stretched out because these guys are pointing different ways, so there's energy there. This is a kind of a two-dimensional example of a type of symmetry breaking which would leave an unbroken symmetry behind with a little bit of energy left over, and we would call that a vortex. And if you just imagine a bunch of vortices stacked up, then that makes a string.
And what features of the early universe correspond to the strings and the needles and maybe even the plane in the example?
Right. So the plane just corresponds to space. Different parts of the plane, where some things fell one way and some the other way, those correspond to very far away parts of the universe that are out of causal contact with each other, meaning that there's no way for a signal traveling at less than the speed of light to have reached from one to the other. So when they decide to fall down, there's no way for them to coordinate. They can't say, like, let's all fall north, whatever that would mean in space. They can't all fall the same way because they aren't talking to each other, so they each have to pick randomly. And then later on, at a later time when more of the universe is in contact, it's revealed that they didn't all pick the same way. Now, what are the needles and the directions and so on? Those would be some field of physics, some new kind of particle that we don't know about, maybe associated with a grand unified theory. So if you take all the theories of physics that we have and you say these should all be somehow aspects of one theory, then everything has to be unified. There have to be new fields that take care of this unification for you. And in many cases, though not all cases, these fields will have the right properties to be like the needles that fall one way or another.
Granted that it's, of course, speculative, but are there any names floating around for what these fields might be, like the inflaton field or other fields?
I don't think so. I mean, they might be the Higgs fields of grand unified symmetry breaking. So we have a Higgs field, and the corresponding particle was discovered not that long ago, which is responsible for a much more recent kind of symmetry breaking, the breaking of the electroweak symmetry. But if there's a grand unified theory, it would also have Higgs particles responsible for breaking it, and that those particles might be responsible also for making strings.
So moving on then, are there also possibly cosmic planes or cosmic solids, or is this just limited to strings?
Yes, no, it's not limited to strings. So you could have domain walls, which are like cosmic planes, where things are one way over here and another way over there, and there's some kind of a plane that separates the two parts of the universe where they're two different ways. You could have monopoles, which are cosmic points. Turns out all grand unified theories give rise to monopoles. And monopoles are a big problem because they form at early times, And then there are a lot of them, and there doesn't seem to be any way to get rid of them afterwards. So they sit around and would contribute a huge amount of energy to the universe that we don't see. So that is called the monopole problem. And the solution to the monopole problem is presumably inflation. Because if inflation comes along after these monopoles are formed, inflation takes some infinitesimal region of the universe and expands it into the entire universe that we can see. And so the monopoles are enormously diluted, so much that we wouldn't expect to be able to see even one. So now the problem is fixed. Cosmic strings don't have the monopole problem because they have another way to lose their energy, which is that the long strings cut each other up in pieces. So when two strings cross like this, they can get reconnected like this, so that you have one going this way, one going that way. So you have a string that comes around in a loop. It can touch itself here, reconnect. You now have a shorter long string and a loop. The loop is now going to oscillate. Gravitational waves get produced. Loop eventually vanishes because all its energy went into gravitational waves, and it's okay. So now we're not left with all the strings that we had way back in the Big Bang. The strings have managed to evaporate. So that's why strings are sort of a good, people are more interested in strings than anything else, I think, because they have some nice properties of this kind. Though people are interested in domain walls too, and there are some, many cases, domain walls can also behave in this way. And those are another possible source of gravitational waves.
So strings, monopoles, domain walls, if theoretically, and tell me if I'm wrong here, they all arise from symmetry breaking events, would we, if we find one, would this, like, if we find a string, would this suddenly raise our credence that, oh, there must also be monopoles and domain walls? Or is it the case that if we confirm one, the others are still totally questionable?
Now, they come from different theories. I mean, the different properties of the symmetry that was broken. So you can have one but not the other. Now, as they say, monopoles, if you believe in grand unification, you always have. But you could have, for example, the formation of monopoles, then comes inflation, the monopoles are all diluted away to nothing, then comes strings, and the strings are still here. So what it really would do, the important thing here is really more that we don't really have any idea about physics, fundamental physics at very high energy scales. So we know, what's going on in physics at the energies accessible to colliders. And then there's, who knows what comes after that? We can make educated guesses. If you found strings, and if we found them now, like if the next nanograv data set discovered strings, these strings would be at the level of 10 to the 13 or 10 to the 14 GeV. Those strings, that would be the first hint of physics at those energy scales. And then we would study them intensively and try to learn what was going on. The other thing which I started on the path toward but didn't mention is cosmic superstrings. So if string theory is right, the fundamental strings of string theory, the superstrings, could be stretched out by inflation to become of astronomical length. Those are a different thing. Those are not symmetry breaking strings. They're not made of anything. They're fundamental strings. They're what everything else is made of. Those would have different properties. Important different property they have is that this reconnection that I said, every time the strings cross, they're going to change partners and get reconnected. This would not happen all the time with superstrings. Depends on exactly the details of the theory, and I am not a string theorist. But people say that depending on the theory, the chance for them to reconnect with each other could be as low as 1 in 1,000. That string network would be different because of that low reconnection probability. So if you had that network with a low reconnection probability, you could distinguish it by some studies from the one with nearly reconnecting nearly all the time. And so you could identify that these are the strings of string theory. That would be fantastic, because I don't know how long string theory's been being studied, 40 years maybe. And we still don't really have any clear confirmation. We have lots of theoretical reasons to think it might be right, but there's no observation. So this would be an observation of string theory in the sky, and everybody would be very excited.